probability of two people sharing a birthday. Well, we're finding the probability that we get a match of birthdays. I'll go ahead and tell you that this year we didn't have a match. Last year we had, last year I think we had 2 pairs match, but then the year before we didn't have a match. But the probability of getting a match, well, we'd have to think about the different possible combinations that are possible for getting a pair. So each possible combination of 2 people that we could have. But the easier way to think about the probability of getting a match here is to find 1 minus the probability of no match. That would be the easier way of doing this, is finding 1 minus the probability of none of them matching. And so that's what we're going to find. Well, we have 28 different people to check. So if I look at my first person, the first person I choose, we're ignoring leap years, by the way, because it just makes it easier. The first person I choose, well, they don't have anybody to match with yet, so they can have their birthday on any day. So they're in the clear to have their birthday on any day they want. But when I go to my second person, if I want to avoid a match, then that means that I need this person to not match whatever day it was that that person had a birthday on. So that means we need 364 out of 365. So they have 364 days to choose from, because they can't match with the day that this first person had. Now, person number three has fewer days to choose from there, because not only do they not have to, they have to not match with the first person, they also have to not match with the second person. So that means they have 363 days to choose from out of 365. Person number 4 now has person number 1, person number 2, person number 3 to all avoid. So they have 362 days to choose from out of 365. And that goes all the way down to the 28th person. And by the time we get to the 28th person, they'll have 338 days to choose from out of 365 in order to avoid matching with everyone else. So I'm going to set you loose on the calculator in just a second, but I want to make it a little easier to put in the calculator. You're still going to have to put a lot in the calculator, but I'm going to make it a little bit easier, because we can get a common denominator here. All of these are out of 365. All of these are out of 365 days. So that means that I can just get that denominator where we have 365, and then the exponent that I can put there, well, there are 28 of these people. And we then can do on the top 365 times 364 times 363. All the way down to 338. So you will have to do a little bit of typing out in the calculator here. Do 365 times 364 times 363 and so on. All the way down to 338. So then get this entire top, everything out on the top, and then you want to divide it by 365 to the 28th. So I'm going to give you about 2 minutes to do some calculator work. Our big fraction here turned out to be 0.346. And so 1 minus 0.346 is going to be 0.654. So when I asked everybody what they thought the answer would be, they said about like a little under 10%. Some people were saying 1%. But the answer is actually 65%. Some more numbers for you on this. And again, it's because there are so many pairs of people that we could have. 23 people is the threshold for having a greater than 50% chance. So if you have 23 people together in a room, then there's more likely than not, you're going to have people share a birthday. If you have 50 people in the room, it goes up to a 97% chance. If you have 60 people in a room, then it goes up to a 99.4% chance that there will be 2 people in that room that share a birthday. So this is part of the reason why probability can be difficult for people, is because our intuitions with probability often mislead us into thinking what the answer actually is. All right. Next problem. And this one in part does have to do with conditional probability. And it's based on a game show. The game show, if you've heard of it, is called Let's Make a Deal. And the host of it, when it originally aired, was Monty Hall. And so that's why this is called the Monty Hall problem. And here is the premise. Here is the pitch. The basic premise of Let's Make a Deal is to offer trades of known amounts for unknown amounts. And so they'll start by picking a person and saying, I have $200 and I could give you $200 right now, or you can have what's inside this box. Or you could trade the $200 away for what's behind that curtain, or what's behind this door. And sometimes it could be a really good prize, and sometimes it could be a really dud prize, and it could be nothing. So here is the concept of one of the things that they would do on this show. They'd say, I would have 3 doors. Door number 1, door number 2, and door number 3. 3 different doors. One door has a brand new car behind it. So you have the chance to win a brand new car. And then the other two doors have dud prizes. Things that you aren't going to want. And so they start by asking you to pick a door. So let's just say, for the sake, we pick door number 1. And they want to, the host wants to ramp up the tension here. They want to make it more intense here. And so they are going to reveal one of the dud prizes. So let's say they open door number 3 and say that it's a dud. Because they're not going to open up the car and let them know that they lost. They're going to ramp up the tension and open up the dud prizes. And they say to you, you can stick with your original choice, or you can change to door number 2. So that's the premise and the idea. And the probability that we're finding is the probability that we win if we switch choices. And here comes the paradox. The paradox is that this answer, the probability that we win if we switch doors, you might think that because we have 2 doors left, that we have a 1/2 chance. But that is not the case. It is actually in our favor to switch doors. We're more likely to win here if we switch than if we don't. So here's the reason for that. The reason is that we know if they opened up a door at random in that second stage of the process, then it would be just as likely to switch. But it is because we know that they are opening up a dud prize that has nothing behind it, that it is more advantageous for us to switch. So let's look at it from the all-knowing concept of what the host sees. So let's say that the car is behind door number 1. So we have the car, not a can, a car. We have the car behind door number 1. We have and we have the dud prizes behind the other 2 doors. And so let's say that when we choose our make our choice, we have the strategy that we're always going to switch doors no matter what. And you'll start to see that in 2 of these choices of doors, we're going to win the car. In 1 of them, we're not. But let's walk through those possibilities. So the first one is the sad situation, which is we pick door number 1 from the start. We pick the car. And so they open one of the dud prizes, doesn't matter which one. So let's say they open door number 3. That was the dud. And we switch our choice to door number 2. And it's the dud, we lose. Next choice, let's say we pick door number 2. Well, if we pick door number 2, then they have to open door number 3 to ramp up the tension and choose the dud. And so then we switch our choice to door number 1, and hey, we won a brand new car. Now, let's say that we choose, same idea if we choose door number 3. If we choose door number 3 at the start, then if we want to ramp up the tension, they got to open door number 2 to avoid opening up the car and giving him that away. And so we switch doors to door number 1, and once again, we've won the car. And so the 2 different ways to think about it is that in both of these situations, you switch to the car because they open up the other dud. And picking that and picking the situation that lets you switch has a 2/3 chance of happening at the very start, door number 2 or door number 3. And the other way you can think about it is that the only way that it's to your advantage to stay with the choice is if you pick the car at the start, is if you pick the car at the very beginning. And that has a 1/3 chance of happening. In the other 2 circumstances, it's to your advantage to switch. And this was actually, when this idea was first published in like science journals and magazines, it got a lot of backlash because people thought there's no way that they don't have an equal chance of giving you the car. There's no way it gives you an advantage, and not just an advantage, but that much of an advantage. But that was the case. And so this has come to be known as the Monty Hall problem.